Okay, so it's time for problem 6.56 on page 187. So this is another problem in physics that students often get confused over, maybe is the best way of saying it. It's the coin on the turntable problem. So the idea is that you have a coin, it's sitting in the center of the turntable, and then the turntable starts speeding up faster and faster, and we want to know, does the coin slide off, or is there enough friction to keep it on? And it seems like, well, gee, how am I going to solve that? Well, the answer is you're going to solve it the same way that we solve all the other problems before this. We're going to draw our force diagram. We're going to apply Newton's second law. Okay, so here's how to think about this problem. Instead of worrying about this 60 RPM and what does RPM mean anyway, we're going to first find the speed v. We're going to find what speed v is the speed where the coin starts to slide off. So when static friction has been exceeded and static friction can no longer provide enough of the centripetal force needed to keep the curved path, then the coin is going to start slipping. So let's determine what that speed is, and then we'll convert that speed to RPM. So RPM, I'll just tell you right now that it's revolutions per minute, and we're going to want to write it as this fraction like this so that we can see our units a little more clearly. But we'll get to that at the end. Okay, so first thing is we need a diagram. So let's draw the diagram so that I'm looking at the edge of this turntable, and here's the coin. All right, so let's look at the forces that are acting on this coin. And you know what? I actually like to put the coin a little, I don't like it right in the center. I know it says it's in the center. I'm just going to put it a little to the edge. Just let me do that. All right. So let's draw the force diagram. We've got the weight acting downward. We've got the normal force acting upward in this case. And if we are to keep this coin stationary, well, even if we're not, there's going to be a friction force in toward the center of the circle. Because if we don't have any friction whatsoever, then the coin would totally fly right off. So we're assuming for right now that it's sticking and that we have static friction here. So it's not slipping right now. Now we are going to figure out what speed is required for it to start slipping, but for now we're going to draw the diagram as if it is not slipping. Okay, well, we know that the friction force is acting in the centripetal direction, causing our curved path. So we're going to apply the Newton's second law in the centripetal version, the mv squared over r version of it. We're going to do the same thing that we did in the last problem. In fact, this problem is very similar to the last problem. Even though the context is completely different, the physics is really exactly the same. So let's look at our forces. We have the friction force, and let's ask ourselves, is that going to be positive or negative, and why? Okay, so that's going to be positive because it's pointing toward the center of the curve, and toward the center of the curve is positive in the centripetal axis. All right, so then that's going to be mv squared over r. And right now, remember, the hint was let's first find that speed v, and then we'll convert it to RPMs. All right. So let's dig out our friction force, and we can make that in terms of mu n. Okay, and then let's go to our other axis. Let's go to the y-axis. And we're going to apply Newton's second law here, but this is not a circular axis. There's no circular motion in the vertical direction. So this is going to be just regular ma sub y. And because we have We have constant velocity of 0, in fact. In the vertical direction, this acceleration is going to be 0. So we have the normal force up, we have the weight down, okay? And that means that the normal force in this case is equal to the weight, and that can be substituted as mg. And let's go over here to this side. I'm going to solve this for v. Okay, so v is going to be all of this. Okay, now let's plug in for the normal force. Okay, that's going to be mg. Okay, now look at our expression. Notice how the masses cancel out. So this is saying that the speed needed to get this coin to start to slide is given by this very simple expression here. And notice that it only depends on the radius of the curve. Okay, so how big is the radius? It depends on the coefficient of friction, how sticky are those surfaces, and then the acceleration due to gravity. Okay, so let's plug and chug. Let's see what we have here. Okay, so we have, oh, I'm sorry, I read that wrong. It wasn't placed in the center of the turntable. It was 15 centimeters from the center. Okay, well, anyway, that's good that I drew it a little bit farther away anyway. Okay, so 15 centimeters from the center to where the coin is placed. So that is the radius of the curve. It's the radius of the path that the object, the coin, takes. It's not the literal dimension of the turntable, because the coin is not placed on the edge of the turntable. So our radius is going to be 15 centimeters. Okay, let's convert that to meters. All right, mu s. Let's see what the static coefficient is up here. And it says that it's 0.80. Okay, so then we can figure out what v is. Okay, so that's going to be 0.15 meters. Mu s is 0.8, and then gravity acceleration. Okay, so let's run the calculator, see what we get. Okay, so to 2 sig figs, it's like 1.08. I'm going to round it to 1.1 meters per second. Okay, so this is not the final answer. This is the speed, the linear speed of this turntable when the coin starts slipping. But we want to find RPMs. So we want to know how many revolutions per minute this is making. Okay, let's do a conversion. So we have our velocity, and we've got 1.1 meters per second. Okay, so now what we want is we want to convert this to RPMs. So that means that, you know what? No, I'm going to do this a little bit different way. Let's start this over. I'm going to show you this way. So so 1.1, actually, no, let me go back.